Ma'am, good morning. Very good morning.
Good morning. Good morning to everyone, and a warm welcome back to the Faculty Development Program of Day 4 on the quantum computing. We are excited to have such a distinguished group of educators, students, and participants who have gathered here today in spite of the weekend day. The objective of today's FDP is to explore new development methodologies and practical applications that can enhance our teaching approaches and deepen our understanding on the emerging subject quantum computing. Before we move on to the today's session, I'm honored to introduce our esteemed guest, Dr. Manjula Gandhi. Dr. Manjula Gandhi is an esteemed associate professor from the Coimbatore Institute of Technology. She is a distinguished expert in the field of quantum computing and education, bringing over 2 decades of experience and a wealth of knowledge to her role. She holds multiple prestigious certifications, including the title of IBM Qiskit Advocate and Certified Associate Developer in Quantum Computation, making her a key figure in advancing quantum technology education. Dr. Gandhi's expertise are extensive. She has made a remarkable contributions in quantum computing, machine learning, reversible circuits, and quantum query complexity, as well as quantum image processing. Her academic background includes master's and PhD in quantum computing, solidifying her technical foundation and leading to years of dedicated research and teaching in this emerging field. Beyond the classroom, Dr. Manjula is a committed mentor, guiding students and professionals alike through her involvement in the IBM Qiskit Advocate Program. She has also organized numerous events, including the CIT Quantum Hackathon and Qiskit India Week of Quantum, to encourage hands-on learning and foster a supportive community in quantum technologies. Notably, she has taken strides to enhance accessibility in quantum education by leading the translation of Qiskit textbook into Tamil, broadening the reach of quantum knowledge to regional language speakers. Dr. Manjula's involvement in the global quantum community is equally impressive. She regularly speaks at international conferences, sharing her insights on the topic such as reversible circuits and quantum machine learning. Her dedication to continuous learning is evidenced by her participation in programs like Wimenium, Global Quantum Program, and various IBM Quantum Challenges. Dr. Manjula's exemplifies a commitment to excellence in quantum education and mentorship. Her leadership in quantum technologies continues to inspire and shape the future generation. I'm happy to welcome such an esteemed guest to share her insights and experiences with us today.
Thank you, ma'am. Thanks a lot for the introduction. Shall I start? I hope my voice is audible to you.
Yes,
Yes.
ma'am.
Okay. I would like to thank each one of you for joining my session today and hope I could give something from my experience, what I've learned, and what was the journey which I have traveled in quantum. And happy to be as part of your FDP. Thanks to all the organizers, committee members, and your HOD sir. So let me share my screen.
Ma'am, sorry to interrupt. Can you turn on the video, ma'am? We will take a screenshot.
My video is on, ma'am, actually. Do you want to off it?
No, ma'am. It is not visible to us, ma'am.
I've on it actually. Can you check now, ma'am?
No, ma'am.
From my side, it is actually visible.
Okay, ma'am. We will have a screenshot at the end of the session, ma'am. You can go on it.
Shall I take, ma'am, from my side?
Okay, ma'am. Okay.
I'm done. Let me copy it in a Word file. Is my screen visible, ma'am? Hello?
No, ma'am. No, ma'am. Your screen is not visible, ma'am.
Ma'am, actually, I've shared my screen. My entire screen. Yeah, also sharing. Camera also. Let me on it. Can you check my name, Dr. Manjula Gandhi?
Ma'am, your name is visible, but your screen is not visible to us.
Right now, ma'am? Now, ma'am? My PPT, I have taken out my PPT and I've shared my entire screen actually.
Ma'am, can you reconnect it again, ma'am? It's not
Okay,
visible to
ma'am.
us.
Let me leave and come back again once.
Yeah, ma'am. Ma'am, now your video is visible to us, ma'am.
Okay, ma'am. Okay. So let me share my screen.
Ma'am, your screen is also visible now, ma'am.
Okay, ma'am. Thank you. So let
Thank you, ma'am.
me start presenting my slides once. So happy morning all. And my today's topic will be design and implementation of reversible circuits using quantum gates. I'm an IBM Qiskit advocate. I'm also an IBM quantum educator. I'm working at CIT for last 24 years. And I'm teaching quantum computing at our institute for last 3 years. And I'm working in quantum from 2003. So let me start off with my session today. My agenda for today's session will be why we are moving into quantum computing, what is the drawback of current day systems, what is the transition from classical bits to quantum bits. The next part of my talk will be different comparison of classical computing and quantum computing, reversible circuits versus irreversible circuits. And the next contents I'll be talking about the various frameworks which are available currently. So maybe some hands-on session, the tools which I'm working on, I can share you the details of how to work with quantum computing algorithms and so on. And the next portion is where all we can use quantum computing concepts. So applications of quantum computing. And then important part of my talk will be how to play or work with quantum states. Quantum gates, I'll be covering single qubit quantum gates, multi-qubit quantum gates. And the last part of my talk will be implementation of some classical to quantum circuits. So basically, I've taken an example of implementing our logic gate and our not using quantum circuits. So that is the my agenda for today's session. Hope I'm audible and my screen everything is visible. Ma'am, just get me a confirmation. So hello.
Ma'am.
Yes, ma'am. Yes, ma'am. Thank you, ma'am. So I'm just moving forward. So why are we moving on to from classical computing to quantum computing? There are some drawbacks which we are having in current day machines. So it is actually quantum systems, quantum computers are something like next generation computers. We have moved from transition from first generation, second generation, third generation, and we have seen the growth of various generations of computers. So again, the need for quantum computers are the first thing is basically, our circuits in current day machines are irreversible in nature. That is, I cannot walk from my output to input. I can construct I will start with our inputs, work with an algorithm, and go back to go to your outputs. But from the output, it is not possible for us to walk in the reverse direction, which is basically a drawback of classical machines. So classical machines, I mean to say that are systems, current day systems. So the advantage of moving from classical to quantum is all your quantum circuits are reversible in nature. So the reason behind reversible is I can have one-to-one mapping between my inputs to outputs and from my outputs to my inputs. So we can walk in both directions. And the what Landrer and Feynman, they were scientists in the period of 1970s and 80s. What they discovered was our transistor sizes are shrinking, and another barrier in our current computers are power dissipations. So the since our circuits are irreversible in nature, we lose our inputs. So some input we are losing, and those inputs are actually generated as heat. So this heat generation is what making our span of our devices, the lifespan of our devices, to be reduced. But if at all, if quantum computers comes into existence, your circuits will be reversible in nature, and we'll have minimized power dissipation. What they have said is, if at all, if you're going for low power design, reversible logic is the one which offers advantages over zero power dissipation, and this is only possible if at all if our computation is reversible. And all quantum computers, basically all quantum circuits, are reversible in nature by default. So the development of computing machines found great success in the last decades, but the ongoing miniaturization of integrated circuits will reach its limits in the near future. So shrinking transistor sizes and power dissipation are the major barriers in the development of smaller and more powerful circuits. So reversible logic provides an alternative that may overcome many of these problems in the future. For low power design, reversible logic offers significant advantages, since zero power dissipation will only be possible if computation is reversible. Furthermore, quantum computation profits from enhancement in this area because every quantum circuit is inherently reversible and requires reversible descriptions. So what is basically a quantum computer is, this is a slide from IBM's quantum computer. So it is a type of machine which uses quantum mechanics principles to perform certain kinds of computations more efficiently than a classical computer can. Normal computers, that is classical machines, uses bits. Basically, we call them as zeros or ones, whereas quantum computers uses qubits called as quantum bits. When I mean to talk about a qubit, it can not only be in 0 or 1, it can be anywhere in between 0 and 1 at the same time. It can also be in 0 and it can also be in 1. So actually, I had a very big fight with my supervisor. Actually, he asked me how a qubit can be in both the states, probably in the period of 2005. I was not having any tool to show how a superposition state will be. I can't visualize it. Earlier, basically, to start off, I started off my research, theoretical research. I started working on query complexities. So quantum query complexities of various graph-based algorithms was my thesis work for my MS by research. And earlier those days, we didn't have any tools or devices or any simulators to work on quantum computing concepts. So actually, I worked on theoretical research, and during 2009, 2010, simulators were available. So my entire PhD I was working on various quantum simulators in the period of 2010 to 2015. And I would say from 2016 onwards, there are various devices which are available. That is, various quantum devices are available. And I've seen this field grow from the child. So actually, from starting from theoretical research, later on moving on with working on with simulators, and now I'm so happy to work on with real quantum devices. I could easily show this is what a qubit is, and this is how, what do we mean by these principles, like the words like quantum superposition, quantum entanglement. All these things I can easily visualize and move on with quantum algorithms, find applications of problems where you can take it out and solve using a quantum machine, which we are not which is impossible for us to solve using a classical machine. For example, if you are from a computer science background, I can take an example of eight queens problem. So design and analysis of algorithms, if you have solved eight queens problem, which is impossible for me to solve, if at all, if I'm talking about n queens, maximum in my machine, in a classical machine, I'm able to solve for an 32 cross 32 chessboard, where I can place 32 different queens such that no two queens attack. But the same thing I can solve using a quantum program for n number of queens. So I'm able to move, or I can say I can take problems which are NP hard problems for us, which those problems can be solved using a quantum machine. And that is why I was now like, even my supervisor told me we'll better leave this area. He told me around 2005. Why not we choose another area and work on, because this is not going to come. It was like that. But since I've done with my all my reviews and seeing the advantages of quantum machines, the only problem which I had in those days was very few experts in quantum computing with the knowledge of computer science background. That was one issue which I had. And we were not having devices or tools or simulators to work on. So those made me, no, I'm not going to move back. I'm just going to continue. And I'm so happy that I'm able to give speak with you all. Like I've delivered last 4 5 years. I'm delivering sessions to various institutes as a speaker, and happy to be part of quantum computing expert actually. So I would promise you that at the end of my session, I can guarantee you that you can take a problem and can solve using real quantum devices. If you're having any questions, please, you can just put a message, or we'll have a question answer session after half an hour. Let me just continue. So a classical computation, we work on classical bits. So it can either be in 0 or it can be in 1. But whereas when I'm talking about a quantum machine, I can be in state 0. This is a block sphere notation. Basically, this is a Q sphere notation. So this is a state, we have a 0 state and we have a state 1, and this is a state which is in superposition state. So what do I mean by a superposition state is I'm in both 0 and 1. That is, I'm in 50 percentage of time I'm in state 0, and 50 percentage of our time I'm in state 1. So at a particular time, a qubit can exist in both zeros and ones, which is impossible for us in a classical machine. So the transition from classical bits to qubits, a 0 state, an upward arrow, a 1 state, a downward arrow in a Q sphere or in a block sphere, and a valid quantum state we represent using quantum mechanics principles called as bracket notation here. This is get notation. A state xi is given by C1 get 0 plus C2 get 1, where this is amplitude. Your C1 and C2 are amplitudes. Your sum of your squares of your amplitudes should sum up to 1. So mod of C1 square plus mod C2 square should be equivalent to 1. So this is what we have in the transition from classical to quantum. I've taken a small example of a scenario here. So just go on with this. So consider we are running a travel agency called as an APC travel agency. He owns 2 cars and there are 3 people. So there are for example, I've taken them as A, B, and C. A and B are friends indicated with a tick mark. A and C are enemies. B and C are enemies. So the idea of this person, this travel agency person, has to allow these 3 people to board these 2 cars, and he has to find which combination of is going to be an efficient one. So if at all, if I'm going to travel with my friend, my journey will be a fruitful one or a happy one. If I'm traveling with my enemy, it is going to be a difficult position for us. So what he has to do is, if both A and B are traveling in taxi 0 is going to be a better one, and both A and B are traveling in taxi 1 is also another solution for this particular scenario. I've taken here ABC are the people, and 0 indicates taxi 0 and 1 indicates taxi 1. So A, B, C. So here we have these combinations. So we have 3 people. So and we have 2 cars. So we have the configurations like 0, 0, 0 to 1, 1, 1. The various configurations. So if I'm meaning to talk about 100, I mean to say B and C are traveling in taxi 0 and A is traveling in taxi 1. Clear? If I'm talking about this, A and B are traveling in taxi 1 and C is traveling in taxi 0. So here I have a formula for calculating this configuration score. Number of friends sharing the same car minus number of enemy pairs sharing the same car. So here if A and B are traveling in taxi 0, so I'm having the number of friend pairs is 1 and there is no enemy pair, so because C is traveling in a separate car called taxi 1. So friend pairs is 1, taxi is 1 minus 0, so we have your score is 1. And similarly, if I'm talking about this one, 110, A and B are traveling in taxi 1 and C is traveling in taxi 0. So we'll have 1 minus 0, which is 1. And for all of the other configurations, we don't have a friend pair in this. So we have 0 friend pairs minus number of enemy pairs is 1. So we have 0 minus 1, which is minus 1 over here. So here for two taxis and for three different people, we have 2 to power 3, which is 8 different configurations which we are having. And by just a small mathematical calculation, we can calculate our configuration score and we can say the solution for this particular scenario is A and B can travel in taxi 0 and C in taxi 1, or another one is A and B can travel in taxi 1 and C in taxi 0, because the configuration score for these two iterations are high comparing to the other ones which are negative 1 minus 1. Moving on with another example. Here I'm just increasing. I'm having 4 people with again some more additional configurations. So A, B and A and C are pairs and combinations like this. So now I'm having 2 taxis with 4 different people. So we'll have 16 combinations here. So the combinations are 0002 1111, meaning that if I'm taking 0110, 0 A and D are traveling in taxi 0 and B and C are traveling in taxi 1. So this is the combination which we are having here. So here the configuration score again, friends sharing the same car minus enemies sharing the same car. So the configuration score, I can write a small C program or a Python program for calculating the configuration score and I can go on. But if I'm increasing it for 100 people, right now I'm not going to take cars and let me take a bus, 2 buses with 100 different people, we'll have these million configurations. So if it is 3 people, we'll have 8 ways. If you're having 4 people, 2 taxis, we'll have 16 ways. If I'm having 100 people with 2 cars, we have 1 million configurations, which is actually impossible for us to solve on a regular classical computer. So solving the same problem with a quantum machine, this is the example for 3 people with 2 taxis. So if I'm going to have 3 different peoples, A, B, and C, and there are 2 taxis, taxi 0 and taxi 1. So I'm calling this to be a qubit. So 000 to 001, 010, 011, 100, 101, 110, and 111. So we have all of these 8 different configurations here, and we have I'm going to compute in a quantum machine. If it is a single qubit quantum machine, I'll be computing on 0 and I'll be computing on 1 at the same time. So this is what superposition is. Computation takes place on both 0 and 1 at the same time if it is a single qubit machine. If it is a 2 qubit machine, I'll be computing on 00, 01, 10, and 11 on all the 4 combinations at the same time. Here, if it is a 3 qubit machine, for all your 8 configurations, so 000, 001, 010, 011, 100, 101, 110, and 111. So we are going to compute on all these 8 configurations at the same time, and I could get a configuration score for 001 and 110 to be the highest one. The amplitudes or the configuration score for these 2 configurations will be high comparing to the other 6, right, other 6 combinations. So we'll be getting a solution of 001 or 110 to be the highest one, and this is going to be my solution. Similarly, if I'm going it for 4 bits, for 8 bits, for 16 bits, for 32 bits, for 100 people, I can just increase. So here, the advantage of quantum is I'm going to compute on 0 and 1 at the same time, something similar to parallel universes. So we are computing on this universe that is on 0, and we are computing on 1 at the same time. So that is the advantage of quantum machines. When I'm talking about the operations here, in a classical mission, for 100 people with 2 taxis or 2 cars, I'll be having 10 to power 30 operations. Whereas when I'm using a quantum machine, the number of operations to solve for 100 people in two cars will be having only one operation. Why? Because my solution is computed parallelly for all of my configurations in one operation of my program. Clear? So this is the advantage of the previous slide was in one single operation, I can compute for all combinations of my configurations, whereas we have some drawbacks in quantum machines. The drawbacks are quantum machines are prone to errors. So there are errors when running a quantum computer. So instead of finding the best solution, it might find the second best solution, the third best solution, and so on. So every time it is not going to give me the best. So first time I'm running off, it might take a configuration score, which is not going to be my best solution. So what is the solution for this is we are not just going to run a quantum program for one iteration. I'll be running it for more number of shots. Say for example, I've written a quantum program. I'll be running it for 1024 shots, and then 1 second, ma'am. Okay. Sorry. So we are going to run it for multiple iterations rather than running it for one iteration. So the operation is we'll be having one operation, but we'll be running the same thing for more number of times. So we will probably want to run the same operation on a quantum computer dozens of times or hundreds of times, and then pick the result, the best result out of the many results we get. So advantages of quantum computers are it is still much better than running the same problem on a regular computer and having to repeat the same type of computation 1 million times. Ma'am, 1 second, ma'am. So comparison between quantum computing and classical computing. Quantum machines work with qubits, which can be either represented with zeros and ones at the same time. So So here, if you could look at this, we are in this is a block sphere representation of a qubit. I'm in 0 and 1 at the same time. Whereas transistors, classical machines work with concepts of transistors, and we can either be 0 or 1 at one particular point. Here, power increases exponentially in proportion to the number of qubits. Here, we'll have power increases a one-to-one relationship with the number of transistors. Quantum computers have high error rates and need to be kept ultra cold, whereas our classical machines work with low error rates and they can be operated at room temperature. The problems which we can solve in quantum machines are optimization problems, your data analysis, unstructured searching, and various simulations. Whereas our machines, classical machines, they are best handled by everyday tasks can be done using our classical computers. So reversible circuits or quantum circuits. So reversible circuits are those circuits that do not lose information. Reversible circuits can generate a unique output vector from each input vector and vice versa. In reversible circuits, there is a one-to-one mapping between input and output vectors. So we have here irreversible AND gate. So this is an example for irreversible AND gate. My value of A and B, if the value of A and B was 0, it is impossible for us to say what was A or what B was, because they can either A can be 0 or 1, B can be either 0 or 1. So I can only walk from my input to outputs, and I cannot walk from my output to input. So this is one drawback of our classical computers, because our circuits are irreversible in nature. Whereas quantum machines are reverse, they have reversible gates. We have one-to-one mapping between inputs and outputs. So here we have A is mapped onto A, B is mapped onto B, and we have a third qubit called as 0. And I'm finding out my output as A and B. This is one of quantum gate. Just note down this gate. We'll later on look into the functionality or the working of this particular quantum gate. So here we have one-to-one mapping between our inputs and outputs. We are not losing any information here. My value of A is retained, my value of B is retained, even from after calculating my outputs. From the end of it, I can also actually walk from the reverse directions. So we have one-to-one mapping, and we don't have any loss of information in case of reversible circuits. So there are various frameworks which are available. Actually, I'm an IBM Qiskit advocate. So Qiskit, the first tool which I started working in 2017, 18 was Q-Sharp. Later on, I started working on with IBM Qiskit. And Classic Platform is another a very, yeah, very nice tool where you can work on with various algorithms, quantum machine learning. If you're interested to work on in the area of quantum machine learning, PennyLane is another tool which is again useful, which is of Xanadu. And Google has Circ and TensorFlow Quantum are from Google's products. Quantum Simulator is India Quantum Simulator, which is developed using CDAC and IIT Kharagpur. So the link for this is this Classic Platform. I'll show you a demo using IBM Qiskit and IBM Classic Platform at the end of my session. So most of my talk entirely deals with working with IBM Qiskit, how to work using quantum gates, build quantum circuits using IBM Qiskit is what my today's agenda is. So these tools are really actually helpful. Applications where quantum computing works on is you can design reversible circuits. So my PhD research was entirely based on designing of reversible circuits, implementing classical circuits, converting them to reversible circuits, and optimizing reversible circuits. So optimization in the sense I can optimize circuits based on the depth of my circuit, length, the width of the quantum circuit, and the gates, how many gates I've used. So actually we can optimize it. I've designed a quantum gate based on my name called as SMG gate. And using that, I've developed some of my circuits as part of my PhD work. So next important applications are many tools are developing. Say Qiskit is one tool, Circ is another tool, uh, Classic. So quantum software is developing quantum hardwares. Devices are actually existing. Each big industries are developing their own quantum computers. So quantum hardware is again, if your younger generation of students, say for example, if you are in your second years, I would definitely say quantum hardware. If you have that too, basically from circuit branches, quantum hardware is a area where you people can work on. And the next portion of my research currently, which I'm working on, is quantum machine learning. All your classical machine learning problems can be converted to quantum machine learning. You can find counterparts of classical machine learning algorithms into quantum machine learning. Quantum image processing, quantum compilers is another area where it is booming. Next is quantum games. So people develop games using quantum devices. And there's a friend of mine, James Weaver. He's one of a senior IBM scientist. He's working on our Carnatic music just to work on quantum music. We were able to write a paper based on, we are actually composing music using quantum gates. And another important application is quantum finance and quantum optimization problems. still there are many things which you can find. All the things which you are having in classical computers, which you can solve using classical devices, can find the counterparts in quantum. That is one of the advantage here, and that made me not to leave, because I thought it will come one day, because I've been to various conferences in India, from IIT Kanpur, IMSC Institute of Mathematical Sciences, Institute of Physics. Earlier those days, I had connects with people from physics and chemistry background. But now I'm connected with n number of people. I'm connected with in advocates program. So I'm connected with nearly 500 Quiskit advocates, wherein when I get a problem where I'm stuck, if I'm stuck with that any of my research, I do get help from various of my friends connected all over the world. And there are many people who are ready to help. The only thing they want is contributions from our side, keep learning and keep growing. So, and that will help the entire community to grow. Okay. So the next portion of my talk is I'm moving on with IBM's Quiskit. So running algorithms on quantum computers essentially involves the following steps. So the things which are required for running a quantum program is we have to pass the number of qubits actually for building a quantum circuit. And then we have a combination of gates, what sort of quantum gates we are using, measuring the qubits and storing the results in classical bits. Where the measurement is actually a problem in quantum machine. So once if I look in, say for example, if I'm in both zeros and ones at one particular state, computing for all 2 to power 8, that is for all 8 configurations, 3 people in 2 cars, I'm computing on all of them in one operation. But once when I measure, when I look into my solution, it gets collapsed. So what we do is we build a quantum circuit specifying the number of qubits, and the circuit is built upon quantum algorithms using quantum gates, and then we measure. And measuring, I'm not going to store it in a quantum bit. We'll be measuring a quantum bit and store in a classical bit. So this is a sample quantum circuit. Let me take my next slide. So here we have, this is a quantum circuit actually. So it is of Q0 goes for qubit 1, quantum bit 0, 1, 2, 3. So this is a 4 qubit quantum circuit, and the last bottom line indicates it consists of 2 classical bits. So this is 2 classical bits and 4 qubits, and each of these lines represent 1 qubit. So Q0, Q1, Q2, and Q3. And all of these are gates, and some operate on 1 qubit and others on multiple bits. So this is a single qubit quantum gate, which I'll be covering in the next part of my talk. So I have X, which is a single qubit quantum gate, and this is CX, controlled NOT gate. This was the one which I showed you for and there in my previous slide. So this gate, we call it as controlled NOT gate. And this is a qubit, this is a symbol for measurement. I'm measuring qubit 2 and qubit 3, and I'm storing it in classical bit 0 and classical bit 1. So this is a quantum circuit of 4 qubits and 2 classical bits. I've not measured Q0 and Q1. I'm just measuring Q2 and Q3, and I'm measuring Q2 and storing it in classical bit 0, and measuring Q1 and I'm storing it in classical bit 1. So each line represents 1 qubit, and these are your single qubit quantum gates, and these are multi-qubit quantum gates, and this is for measurement. So continuing, representing qubit states, we use direct bracket notation here. Quantum states are represented using vectors, and for state 0, this I read it as gate 0. Gate 0 is represented using 1, 0, and gate 1 is again a column vector which we represent it using 0, 0, 1. If it is a superposition state, I mean to say I'm in both the states, 0 and 1, 50% of time. So 50% of time I'm in state 0, and 50% of time I'm in state I. This is again I1. This is another superposition state. I'll tell about this little later. And when I mean if it is a superposition state, I'm not going to be in fully 0 or fully 1. we are partly in 0 and partly in 1. That is 50% of time I'm in state 0 and 50% of time I'm in state 1. So with this again, quantum states are represented using three basis states. We have Z basis, Rx basis, and Y basis. So Z basis, I mean this is a block sphere here. A Z basis, I mean I'm in state 0 and I'm in state 1. When I'm talking about X basis, we are in state plus and state minus, and this slanting one. Y basis is horizontal line where we are in state I and state minus I. So state I and state minus I and Y basis, we call them as clockwise and anti-clockwise rotations. So basically we'll be using a Z basis, that is gate 0 and gate 1. Top line indicates 0 and the bottom arrow indicates 1. And the other one is superposition state. I'm not in 0 and 1, I'm in both zeros and ones. So this state indicates I'm in 0 plus 1 divided by root 2, which we indicate it using a state plus. And the state opposite to this line is actually minus state. I mean to say I'm in gate 0, that is 0 and 1 uh, in combinations of zeros and ones with a phase change in for 1, the negative phase change. I'll show this in visualization. So representing qubit states, qubits can be represented by two-dimensional vectors, and this is a general notation for qubit. Get 0 is given by cos theta by 2 0 plus ei phi sine theta by 2 get 1. This angle is your theta value and this angle is your phi value. So a generalized qubit state is represented using this get notation. So let me show off with a demo of working with IBM QuizKit. So my first demo will be playing with quantum states. After this demo, let me have a question answer session if you're having any doubts. So this is quantum.ibm.com. Hope this is visible. You can just type this in Google. And if you are a first time user, I hope my screen is visible here. You're a first time user. Ma'am, is my screen visible?
Yes, sir. Yes, ma'am. Yes, ma'am.
Okay,
It's
sir.
visible.
Thank you. So if you're a first time user, you can create an IBM ID here. Or since I do have an ID here, I'm just continuing with my IBM ID. So continue with the IBM ID. I'm just clicking off this. My ID here. I'm at the bottom. There is something called as IBM Quantum Composer. I'm taking this composer. So let me open file a new circuit. I don't want QPUs. I'm just closing all of this. So earlier quantum devices were free, so we can use them without any quantum processing unit. But right nowadays we have to pay and use devices. But Composer is free, so you can work with these composers to visualize if at all if you are in the beginning of quantum things. If you are in the early stage of quantum computing. So here I have a quantum circuit. Let me, this is for qubits, Q0, Q1, Q2, and Q3. I'm just deleting some of my qubits. So I'm just keeping it on Q2 and I'm deleting this. I'm again keeping on this and deleting it. Again, this C4 indicates this is classical bit. So I'm just deleting classical bit here. And this is Q0 and Q1. Let me take a gate called as, this is NOT gate. And look at the bottom of the screen here. So if you could see here, I've just taken out this particular state. So what I'm having, just look at this. This is probabilities one. So Q0 is actually, I've inverted it. Initially, by default, all qubit states will be in state 0. So let me add 0 here, another 0 for Q0 and Q1. And I'm inspecting this particular quantum circuit to show you what is actually happening. So let me start off. Initially, I'm in state 0, 0. So Q0 is in state 0 and Q1 is also in state 0. So the probability here, we are in 0, 0, 100% of time we are in 0, 0. And your Q sphere is actually, we are in state 0, 0 for a 2 qubit mission. And your state vector notation, these are various output representations actually. So here again, we are in state 0, 0 at fully 100% of time. Okay, and now let me move on. So I'm adding a NOT gate here. So if I've added a NOT gate here, what did the do is I'm inverting my Q0 from 0 to state 1. So this becomes, this is 0 and this is 1. So you will read your quantum states in Qiskit using little endian notation, where this is Q, this is 1, your left end, sorry, your right end is your Q0, and then your next one is Q1. Say, I'm just stopping off this. Let me add another qubit here. So increase it, Q1. I'm adding a plus sign to this, and I'm also adding a 0 here. So this is how I work. I increase. Composer works for maximum of 5 qubits. And so this is for a 3 qubit mission. Again, let us inspect this. I'm starting from 0, 0, 0. So initially, all my 3 qubits are in state 0, 0, 0. This is an example for 3 people traveling in 2 taxis. So taxi 0 and taxi 1. And if A and if suppose if this is A, B and C, next portion is I'm moving on with this has become to 1. Your Q1 is 0 and your Q2 is 1. So this is 1, 0, 1. Okay. So this is how you play with your quantum states here. Say for example, I can drag and drop whatever gates I want. So if this is 0, 1, 1, A and B are traveling in taxi 0, and so A and B are traveling in taxi 1 and C is traveling in taxi 0. So this is the case here. So this is 1, 1, 0. Your Q0 is 1, your Q1 is 1, and your Q2 is 0. Okay, so this is how you play with your quantum circuits. There are many gates which are available. This is one of the quantum gate which which we'll be looking at later. And this is for measurement. I'm measuring. So on measure, I'll be actually measuring. Will collapse. Will either get 0 or 1, even if I'm in a superposition state. Okay, that I'll show you how to create superposition states little later. And this is CASM code, which is automatically generated. Whatever changes we do here is actually reflected in the other portion of my code. So we have open CASM 2.2, include a library file here. We have created 3 quantum registers and we have 2 classical registers in this example. Q0, I've resetted it. So first time when I've done these 3 things, I'm resetting Q0, I'm resetting Q1, I'm resetting Q2. I'm applying X gate on Q0, I'm applying X gate on Q1, and then I've applied CX gate. I'll talk about these gates a little bit later. I've applied CX, and then I'm measuring Q0 and I'm storing it in C0. So this is what our work has been done here actually. So we are working out with this, and we can measure our outputs after running. We just measure it. Right now, the setup and run, there are some changes because of Qiskit 1.2, which was released recently. And there are quite a few changes which are made. So we can't run it on real devices here, but we can install Qiskit locally, and you can run your program on real devices if at all, if you're having a quantum processing unit of various providers, either from IBM's or from NVIDIA's or Google's, whomever devices you're having, you can work with those. But for learning purpose, I would suggest it is enough if you work using Composer, practice with your quantum gates and build classical circuits, convert them and work on. So if you're having any doubts, you can ask me here. Ma'am, any doubts?
Just a minute, ma'am. Participant, if you have any doubts, please raise your hand. I will unmute you.
Sir, if no doubts, let me continue with my slides.
Yes, ma'am, we can continue. We do the end of session. We will have
Okay, sir. Thank you. So the next portion of my talk is single qubit gates, which we are working on. So these gates will be working using quantum composer. I actually the X gate, which inverted my 0 to 1, and it will invert my 1 back to 0, is your X gate, which performs a rotation of pi around X axis. Your Y gate, we call it using QC. QC is a quantum circuit dot Y. Here, this is my Z gate. And next we have S gate, we have S dagger, and we have Hadamard gate. So Hadamard gate, a very important quantum gate. I'll show you the matrix representations of these gates and how these quantum gates can be worked to build quantum circuits. So we'll be looking with these quantum gates. Basically, your X, Y, and Z, we call them as poly gates, and they have their own inverses. What do I mean by their own inverses? If I'm applying X gate, again, if I'm applying X gate, it will behave. Say, for example, I'm starting from 0, I apply X gate, it converts to 1. Now again, if I'm applying X gate, it moves back to 0. So I started with 0, applied X gate, converted to 1. Again, I'm applying X gate, converts back to 0 again. So this is what we have. We mean to say that these polygates X, Y, Z have their own inverses. So Y is also will behave exactly the same way. But your Z gate does not have its own inverse. We also have a gate called as T, and S and T are non-poly gates, and they don't have their own inverse. So we have something called as SDG, or we also call them as S dagger gates. And then we have our Hadamard gate. Hadamard gate, I'll show you here. So I want you people to a very important slide. If you're really interested to work on quantum gates, building quantum circuits, this slide will be an important one. So initially we have these things. So a plus state is indicated by 1 by root 2, 0 plus 1. So I'm in 50% 0 and 50% 1. A minus state indicates the representation of a minus state is 1 by root 2, get 0 minus get 1. This is for X basis. If you remember this particular slide, my X, Y, and Z basis. So my Z basis is 0 and 1, and my X basis is plus and minus. So plus and minus is 0 and plus and minus is 0 plus 1 divided by root 2 and 0 minus 1 divided by root 2 for X basis. And for Y basis, we have Z, what is that, I and minus I. So 0 plus I 1 divided by root 2 and 0 minus I 1 divided by root 2. So most probably we'll be actually working with your Z and X basis in for today's session. So here my X gate. So this is for X basis plus and minus. This is I and minus for your Y basis states, and this is your X gate. So X gate matrix representation. So X 0, 1, 1, 0. And the various bases which we are having is 0 and 1 for your Z basis states. Plus and minus are your X basis states, and your I and minus I are for your Y basis states. So what will happen if I'm applying X on 0? It will take me to 1. What will happen if I'm applying my X gate on 1? Takes me to 0. What will happen if I'm applying my X on plus, X on minus, X on I, X on minus I? This slide, after mere working, we have represented all your outputs in one single slide. So the various inputs I'm taking a 0, 1, plus, minus, my I and minus I, and applying X gate onto them. Similarly, this is your Y gate matrix. If you are interested, please note down the matrix representations of X gate, matrix representation of Y, matrix representation of H. So what will happen if I'm in 0, I'm applying Hadamard gate. Your H goes for Hadamard gate. H on 0 will take me to my plus. So I can convert from one basis to another basis. Say I'm in state 0, which is I'm actually in Z basis. I want to convert my Z basis to X basis. So what should I do is I have to apply Hadamard on 0. So it takes me to my plus basis. Similarly, if I'm in state 1, if I'm applying H gate, it will take me to my minus state, which is 0 minus 1, the whole divided by root 2. So X, Y, this is your Hadamard. Next gate is your Z gate. So the matrix representation for Z gate is 1, 0, 0, minus 1. Again, the various inputs. So Z on 0, what does it do? Z on 1, Z on plus, Z on minus. So where, what does it do actually? So Z on plus, it takes me to minus state. Okay. And we have S gate here. S gate, say for example, if I have a plus state, Z on plus takes me to I. So like this, you can move on with various inputs to outputs from one basis to another basis by applying various quantum gates. So I'll just show these demos of single qubit quantum gates using Composer here. So let me just delete this. Deletion is just select and delete. I'm coming over here. I'm just clicking on this, deleting it. Let me take a new qubit, just single qubit gates. So I just don't want more number of qubits. I just need one classical bit and one quantum bit is enough for me to show the various quantum gates which you have seen in my slides. So the first one is X gate. So I'm here. Again, I'm applying another X gate. Let me start with reset here. So 0. Let us inspect this. Look at the probabilities section here. So I'm starting. Initially, I'm in state 0. Okay, I'm in state 0. Now, after plus, that is, I'm moving from 0 to 1. And again, I'm applying plus gate, that is X gate. So it takes me back to 0. And I'm stopping off. So the final output is going to be I'm in state 0 here. Okay, I'm in state 0. So this is your vector representation for state 0. So 0 is represented by state vector representation 1 plus 0j plus 0 plus 0j. Actually, Qiskit is built upon Python. So we have your amplitudes represented using j here. So 1 plus 0j and 0 plus 0j. So like this we work on. I'm just stopping off my inspect and let me take a Hadamard gate here. So let us delete this. Let me take a Hadamard gate. So what is actually happening on my Hadamard gate? So the state vector representation of Hadamard, I'm in 50% 0 and I'm in 50% 1. So here, this is 50 percentages actually 0.707 plus 0j plus 0.707 plus 0j. This is for state 0 and this is for state 1. So we are in 50% 0 and 50% 1. So look at the QASM code which is generated. We have a quantum circuit of 1 qubit, classical circuit of 1 qubit, and reset of q of 0. And I'm just starting on this is reset line. This is optional. And I'm applying Hadamard gate on Q0. So what does Q0 do for me is I'm putting a qubit in a superposition state. Your Hadamard gate actually puts in a superposition state for us. So again, let me take another Hadamard. And if you're inspecting this, again, H is also reversible in nature and it is unitary also. So we are starting from state 0 here. Moving on, I'm applying Hadamard. So it takes me to 50% 0, 50% 1. Again, I'm applying Hadamard. So it takes me back to state 0. So it takes me back to state 0. This is what I mean to say. So we have started from 0. I've applied a Hadamard gate. So h on 0, where does it take? It takes me to plus. So plus in the sense I'm in 50% 0 and 50% 1. So that is 1 by root 2 get 0 plus get 1. So this is how your single qubit quantum gates works. Any doubts in single qubit quantum gates? Anybody? If I want I. Okay.
Ma'am,
Yes, sir.
I'm doing. Okay, I have a small doubt. Is there any tool for free tool is available for checking the circuits?
For checking.
Uh, so for doing this process, is any free tools are available, ma'am?
So this itself is free only, sir.
Free, ma'am. Okay. Okay.
Yeah, this is free. The only thing is you
I,
have
I
to.
thought it's an IBM, so it is a
No,
price.
no, no, no. It is free for everyone. You can use it.
It's a free for everyone. Okay.
Yeah, yeah. This is a platform actually, IBM Quantum platform.
Okay.
It will take me here actually. If you're a new user, you can create a new ID. It is free, sir. You need not spend money.
We know. Okay.
This is free. This is free. There is another tool called as Classic, platform.classic.io. This also I'll be showing my demo at the end actually. This is also
Okay.
free. All the tools are free, sir. Actually, initially they are free. You need not for learning. You need not pay anything.
Okay. Okay. So few
Okay.
more participants have a doubt, so I will
Yes,
enable
ma'am.
for you.
Yes. Sir, will they be
Good
asking?
morning, ma'am.
Yes, yes, ma'am.
Ma'am, very nice presentation,
Thank you, ma'am.
ma'am.
Actually, the
Ma'am,
thing
in
is,
for my
yeah.
doubt in qubit statement, ma'am,
Hmm.
how can combination of single qubit gates
Hmm.
approximately any possible rotation or operations?
This is actually rotations, ma'am. Like we are converting from one basis to another base.
Okay,
Say
ma'am.
here if I'm taking my the block, this is actually your. Is this visible, ma'am? Q sphere.
Y- Yes, ma'am. Yes, ma'am.
Yes. So here, if you could see, if I'm actually, if I'm deleting this, initially I'm inspecting it. If you could see, we are in state 0. Let me start. I'm in state 0. Okay. And I'm now, as I told you, we can compute on both zeros and ones at the same time. How was that? How was that possible? Is that is only possible because of your Hadamard gate. So you start from state 0, you apply your H gate will convert, it will put your qubit in 50% 0 and 50% 1. So I'm here in a combination of both the qubits here, both the states,
Okay, ma'am.
0 and 1.
Okay, ma'am.
So here,
Ma'am, and also
hmm,
how it relate to multi-qubit operations, ma'am?
well, yeah, that's a very nice question, ma'am. Let me add another qubit here. Let us go for a 3-qubit machine. Okay, so 3-qubit machine, if you're looking at your Q sphere, it will look like this. And your state vector for all 8 combinations, as I showed you for 0, 0, 0, your 3 people traveling in 2 cars. We had 8 combinations, right, ma'am? So 2 to power 3 states. So 8 ways we have. So I can apply Hadamard on all of my qubits. So let me put here. Let me also start with 0 here. Zeros here. So this is 0, 0, 0, 0, 0, 1. I'm in all 8 combinations at one point of my time. If you could see, the value, the amplitude value is equally divided. It is 0.354. Okay, for all 8 combinations. So we are computing on all of these 3 qubits at the same time.
Okay, ma'am. But when would it be used, ma'am?
When?
We when we will apply this?
Whenever you want to compute on multiple states,
Okay,
multiple values. So if I
okay,
want to compute for all combinations of 2 to power 3, that is here, since I'm having 3 qubits here, I'll be having 8 combinations. So if I want to compute, if at all, if I'm having a problem, if I'm talking about if it is an n queens problem, if I'm going for n number of qubits. Say one thing which I would like to talk here is if I'm having a 3-qubit machine, I'll be having 8 combinations. So I can compute on all of my 8 values in one point of my time. Similarly, if I'm having a 32-qubit machine, so 2 to power 32 values, imagine the amount of combinations I'll have. If it is a 127 qubit machine, so 2 to power 127 values I can compute at one particular time. So how do I compute at one particular time? When I'm applying Hadamard gate on my all of my qubits. So if I've applied Hadamard on all of my qubits, I can compute on all of my states at the same time, parallelly.
Okay, ma'am. Thank you.
Yeah.
Thank you.
Thank you. Thank you. So any other doubts?
Yeah, ma'am. Very good morning. This
Good
is from
morning.
Velumani. Yeah,
Good
Velumani.
morning.
I have one more doubt.
Yeah.
Actually, you gave the difference between the quantum computing as well as the classical computing. So I have one more doubt. So how can incorporate the quantum computing, especially in cybersecurity, madam? Is it possible?
Yes, sir. Yes, sir. Cybersecurity, quantum cybersecurity, post-quantum cybersecurity, everything is actually available. We have quantum key distribution actually. Again, it is I would say quantum is something which you can find counterparts of all your classical things. So you can bring in there are two famous algorithms. One is Shaw's factoring algorithm. The other one is Grover's search algorithm. It was found in the year 1992 and 1994 respectively. After these two algorithms came into existence, people started digging into quantum computing actually. So earlier in 1990s, no one were there were people, there were physics people who were working in quantum devices, but uh, it came into existence and people started researching only after these two algorithms. What do they say is factoring algorithm, Shaw's factoring algorithm, are current day cryptography techniques. Our passwords are rightly, actually they are, we are unable to hack because you cannot factor a very big number, right? But whereas when I'm talking about a quantum machine, if it comes like as we are using devices right now, classical devices we are using, everyone are using. But if quantum devices really comes into existence and people start using, you can easily hack your passwords. You can break your passwords. So quantum cryptography is a major area where people are really working on, and they're also working on post-quantum cryptographic algorithms. So what will happen if quantum systems comes into existence? Something like quantum resistant algorithms, which can withhold even if quantum devices comes into existence, are cryptographic techniques to be safeguarded. So you can easily dig on, you just browse for papers. There are plenty amount of papers available for cryptographic techniques also.
Thank you. Just a minute. One more. My colleague is also want to ask some questions.
Yes.
Just a minute.
Hello, good morning, ma'am.
Good morning, ma'am.
Ma'am, very good presentation.
Mhm.
Ma'am, my question is how it is what are the applications can be used in the quantum computing, and whether it is applicable for machine learning
Yes,
concept?
ma'am.
Yeah.
Quantum machine learning, there are again I could say, as I told for cryptography also, quantum machine learning, there are very our Indian people, many of them are working on quantum machine learning. Quantum machine learning, you could get plenty of research papers available. Olivia, people, there are actually, I can show you at the end of my references for quantum machine learning. Even I have a GitHub repository where we have worked on a collaborative project on quantum machine learning with my other advocates.
Okay.
So you could find n number of papers. So anything which you have worked on classical machine learning, you can take and implement it using quantum, and you
Okay.
could show the accuracy of it. There are some cases where we are able to get a better accuracy in classical machine learning itself. We are able to not to get higher accuracy. It is not possible. But there are algorithms or there are papers which are available, and wherein you can improve your accuracy also.
Yes, ma'am. Now, currently, can you say any applications which is used in the quantum computing?
Like I've worked on prediction of course outcomes for our students, ma'am. So
Oh, okay.
CU attainment. we worked on classical algorithms and then moved on with quantum algorithms, quantum machine learning concepts basically. So we solved the problem for attainment of course outcomes for classical machine learning and showed the improvisation using quantum machine learning. This was one.
Fine. Thank you, ma'am. Thank you so much.
Okay. Thank you, ma'am.
Ma'am, one more question. Hello.
Yes, ma'am. Yes, ma'am.
Ask by another ma'am.
Ma'am, I'm able to hear you. Yeah.
Okay, ma'am. Good morning, ma'am.
Good morning, ma'am.
Ma'am, different classical quantum computing, ma'am.
Ma'am, I didn't get your question. Yes, ma'am. Once again.
What is the different classical difference between quantum computing, ma'am?
What is the different classical?
Computing, ma'am. Quantum computing.
What is the different?
Classical and quantum computing.
Difference you're talking, ma'am? Difference between quantum computing and classical computing you're talking, ma'am?
Yes, ma'am.
Okay. Difference between quantum computing and classical computing, I would say quantum computers are reversible in nature. So you can walk from inputs to outputs and output to input, both the directions. And I'm able to compute on multiple values at the same time because we have superposition states here. We have another feature called as quantum entanglement, where what is entanglement is I can entangle two qubits, just like if you have heard twins behave exactly the same way. One twin here, he will also behave in the same way in another other side. The same thing we can do for qubits also. We have a single qubit here, entangling two qubits, throwing one in one universe, throwing another in another universe. So what happens is, looking at this qubit, I could predict the output of the other qubit without even visualizing it, without even measuring it. So here, look, sitting in my in India, I can measure another qubit in US, something like
Okay,
that.
ma'am. Okay, ma'am. Okay,
That is entanglement. So actually, you can solve all your NP-hard problems in quantum machines. Only thing is we have to find and dig into things, papers which are already existing.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am.
Good morning, ma'am.
Good morning, sir.
Actually, since we are using 2D vectors to represent the qubits, why are we using a 3D space like block sphere to represent it? Wouldn't be a circle more common to represent the qubit?
Yeah, sure. Very good question, sir. So actually, qubits are not just Qiskit uses. We have one representation called as Q sphere. This was the one which I showed you here. This is Q sphere. Okay, this is a vector state. Where there are other representations which is represented by Qiskit actually. So block sphere is another representation. These are various representations. You can use whatever you're interested in. If you're interested in a 2D vector representations, you can go for Q sphere. If you want output in a block sphere representation, Qiskit is actually a tool where you have the various vector representations. One is probabilities, you have Q sphere. Block sphere, I can't show you in Composer. It is not possible for me to show you here. But I can show you, if you give me 2 minutes of time, I can show you block sphere using my local demo actually. The representations. These are representations which are supported by Qiskit, not by all quantum devices. So it is up to us to use whatever representations we want. But we use vector representations. Vector representations, we'll be representing it like this. All your 8 combinations. If you look at this, let me just copy this in a clipboard and if I take it is something like this. So this is a state vector representation for all combinations. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So for all 2 to the power 3, that is 8 different values, I'm putting in a superposition of all of my 3 qubits. So all your 3 qubits are represented this, and this is your state vector representation. This is one way of representation. I can also represent this using a histogram. I think histogram representation will be, this is your histogram representation. So all your combinations, so all your 8 states as your solutions. And this is your Q sphere. These are various output representations of Qiskit also. Clear, sir?
So then, in a Q sphere, on a certain latitude, like all the qubits which lie on a certain latitude will have the same superposition, right?
Will have the same superposition. Okay, maybe. See, I'm actually putting it, since this is too complex here, let me delete this and show you. Here, if you could see, I'm just showing it for, I don't want this qubit also. Let me have a 2 qubit, so that is easy for you. This is 0, 0. This is 0, 1. This is, sorry, this is 0, 0. This is 1, 1. This is, my right end is 0. Okay, so Q0, 0, 1, and this is 1, 0, 1, 0. So for 2 qubits, what was your question? Since it is in superposition state, I'm showing for all combinations. So 2 to power 2, all 4 values are shown here. If they are not in a superposition, if this is not in a superposition state, I'm in state 0, 0. Both my qubits are in 0, 0. If I'm inverting 1, you could see I'm in state, my qubit 0 is in 0, my qubit 1 is in 1. So this is 1, 0. Clear? If I'm taking this, yes, sir?
Actually, what I'm asking is, like we represent the qubit in the Bloch sphere, where like each qubit lies on the surface of the sphere.
Not just the surface, it can be anywhere.
Oh.
It can be anywhere. 1 second, if I can. I need 2 minutes to load it. Actually, I thought of Bloch sphere representation. 1 second. Sure. The Bloch sphere, it can be anywhere in between zeros and ones. 1 second, 1 second. Okay, let it load, sir. Keep this in mind. I'll show you my Bloch sphere outputs. Well, Bloch sphere I'm not having here in Composer, but I'll show you my local demo. Let it get loaded actually. So meanwhile, any other questions?
Okay, ma'am, we can continue the sessions. And the end of the session.
Yeah, yes, yes. Let me take another one which I have. Okay, let me show you the Bloch sphere output little bit later because I thought it was not. So from my current slide, so single qubit gates, and the next portion of my talk will be multi-qubit gates. I'm just not going to go into theoretical portions of these things. So this is multi-qubit states. Multi-qubits for 2 power 2 qubits. So if it is 2 qubits, we'll have 2 to power 2, that is 4 different values. And my amplitudes A00, A01, A10, A11. For a valid quantum state, it should be the sum of the squares of your amplitudes should sum up to 1. So A00 square plus mod of A01 square plus mod A10 square plus mod A11 square should sum up to 1. This is a valid quantum 2 qubit state. So the next, this was one of the CX gate. I'll show you this in a demo. What does this do is, we have top line is control qubit and the bottom line is target qubit. If your control qubit is 1, your target qubit will be flipped. If your control qubit is 0, your target qubit will remain unflipped. So this is the working of this particular quantum gate. And the gate function name is CX actually. And this is the notation of CX gate. And this is the truth table of CX. So if my input is 0, 0, my output is 0, 0. So that is why it is 1. My input, if my input was 0, 1, my output is also going to be 0, 1. If my input is 1, 0, the third line, this is 1. Your first qubit is 1 and your second qubit is 0, my output will be 1, 1. If my third qubit is 1 and my fourth qubit is 1, my output will be, that is for input 1, 1, my output will be 1, 0. So this is what we have in CX, and this is used for entangling qubits. So what do we mean by entanglement is, suppose if I have entangled qubits like this, and I'm throwing one in one universe and another in another universe, both the qubits will behave exactly the same way. Okay, that is what quantum entanglement is, and this CX gate plays a major role in entanglement, quantum entanglement. This is CZ gate, the matrix representation. CZ gate, exactly the same way. If your control qubit is 0, the target qubit remains unchanged. But if your control qubit is 1, you will apply, instead of X gate, you will apply Z gate. What does Z gate do is, for 0, it doesn't do anything, but for 1, it changes to -1, if you remember this. So Z on 0 does not do anything. Z on 0 remains 0, but for Z on 1, it changes to -1. We have a phase change here. The negativity is -1 over here, -1. So ZZ will apply control Z if it is, if your control qubit is 1. So that is, if my control qubit is 1, I'll apply Z gate on state 0. So 0 remains 0 itself. If my control qubit is 1, it will apply target Z gate on 1. So 1, 1 is actually changed to -1, 1. This is how your CZ gate will work. I'll show the demo here. This is for swap. I can swap two qubits, Q0's, Q1 values. We can swap it out and show. And this is for C-swap Fredkin gate. Again, this is a multi-qubit, 3-qubit quantum gates. If your control qubit is 1, we'll swap qubit, the next two qubits. If this Q0 is 1, Q1 and Q2 are swapped. If this Q0 is 1, my 1 and 0 are swapped. So my output will be 1, 0, 1. For here, my output will be 1, 1, 0. Okay, this is how your C-swap gate works. Next is Toffoli, and this was the gate which I've used in the first demo, for first part of my reversible circuits. So if this is 1, 1, 0, my output is going to be 1, 1, 1. What do we have here is two controls and one NOT gate. If both the controls are 1, your target will get flipped. So the only change which we'll have here is 1, 1, 0 will change to 1, 1, 1. And if my input is 1, 1, 1, my output will be 1, 1, 0. Okay, this is how your C0 gate works. So we'll see the demo using multi-qubit quantum gates. 1 second, if I can take. Just a minute, sir. Sure.
Okay.
Demo of multi-qubit quantum gates. Let me show it in local demo. Rather than showing it in Composer, let me show these things here. I think probably I have a block screen here. Yeah. This is, I've installed Qiskit. I've installed Anaconda. Upon that, I've installed Qiskit, imported the versions of it. Okay, there are some, this actually, this is the older version of Qiskit. Newer version has some minute changes. Okay, so this is your CX gate. If I'm writing code, QC is equivalent to quantum circuit of 2, 2, indicating the first one is your quantum bits and the second one is your classical bit. So we are building a quantum circuit of 2 qubits and 2 classical bits. And I'm applying CX gate on 0, 1. So QC dot CX of 0, 1, and I'm drawing this using MPL stands for Matplot library. I've included it and I'm drawing it using this. So here, what does the CX of 0, 1 do? So what we are doing it, and I'm measuring 0, 0, storing qubits, measuring qubit 0 and storing it in classical bit 1, measuring Q1 and storing it in classical bit, second classical bit. And for executing it, right now there are some changes at the back end. So this you need not worry about this code. I'm executing it using my state vector assemblator here, and my output is, since I've given 0, 0 as my input, my output is also going to be 0, 0. I've applied CX gate, but there is no change over there. Why? Because can anyone see me if you have understood my session? I have CX here. I'm just removing this. So we are starting from state 0, 0. Let us put 0 here. 0. Composer is actually easy for the beginning at the earlier stages. So 0, 0. Let me inspect it. Okay, I have to reset. Let me delete it. So I'm just inspecting it. I'm starting with 0, 0. So I'm in state 0, 0. Moving on. Now I've applied CX here. So since my control qubit is 0, my target qubit is also 0. There is no change. We'll only be, the final output will also be in 0, 0 only. Okay. If you want, you can add measurement. I'm adding a classical bit also. I'm adding a measurement. So my measurement will also be 0, 0 only. But what happens here if I'm inverting this? So my input here was, can anyone tell me what my input is? If I start, we start from 0, 0. We are moving here. We are now changing to Q0 is 1. Your second qubit is 0. Okay, this is 1, 0. Here, this is 1, 0. This is 1 and this is 0. In now coming here, this is 1 and this is 0. So if my 1, 0 is my input to my CX gate, my output is going to be 1, 1. My control qubit is 1. My target qubit will get flipped. So we'll have 1, 1. And next I'm measuring it. So measuring will also give me state 1, 1. Clear with this output? If this was, let me close my inspect and again I'm going with 1, 1. What will be my output? Starting here, let me just walk out 0, 0. Here it will be 1, 1. Now after CX it is going to be 1, 0. My final output is also 1, 0. Let us inspect this. Starting 0, 0. Next is 1, 1. Okay, so because I've applied X gate on both the qubits, so it is 1, 1. Now I'm applying CX on 0, 1. So it becomes, your top line is 0, your top line is 1, the that is Q0 is 1, and your bottom line from 1 it is being converted to 0. Why? Because my control qubit is 1. If your control qubit is 1, your target qubit will get flipped. So this becomes 1, 0. Your measurement will also lead to the same thing. Clear? Is this, are you able to follow me, sir? So this
Yes,
is
ma'am.
how
Yes.
your, this is, so for the same, this is your Q sphere output, 0, 0. So here, block sphere, actually, I can have values. One of you asked me, is it going to be on the outer space of your block sphere? No, I can have values anywhere here, anywhere in my block sphere. So all three, anywhere combinations we can have. And a block sphere will show for qubits separately. For Q0, I'll have one block sphere. For second qubit, I'll have another block sphere. Whereas Q sphere will show output for both the qubits in one Q sphere. So this is a two-dimensional visualization, whereas block sphere is a three-dimensional view and shows for individual qubits, Q0, Q1 separately. Okay, I hope I answered your question. So this is your histogram output. So if I'm going to execute the same program which I had 0, 0 as my input, my output is also going to be 0, 0. Look at this. My input is 0, 1. My output is also going to be 0, 1 for this particular quantum circuit. I hope I'm running fast, but so this is 0, this is 1. Clear? Q0 is 0. Since my control qubit is 0, my target qubit remains unchanged. So we'll have 1, 0 and 1. So this is Q0, 0 and your second qubit is 1 in your Q sphere. This is your histogram output. CZ gate. So I'm applying X on 0, I'm applying X on 1 and I'm applying CZ on 0 and 1. So what will CZ do is, if your control qubit is 1, it will apply Z gate on Q1. So it will become, my output will be, any answers please? My input is 1, 1. My output will be, I showed in my slides also. My input is 1, 1. Control qubit is 1. Your target qubit you will apply Z gate on this 1 also. But for 1, if I'm applying Z gate, it will change 1 to -1. So my output will be -1, 1. Okay, so look at this is your block sphere. Block sphere does not show phase change. That is negative, it will not show. Q0 is 1, Q1 is 1, but we had -1, 1. So look at your Q sphere output. This will be in a different color if you're running in your machine. My machine, I think there is some issue. So we'll have -1 in a different phase change color. Show you different phase changes somewhere. So this is swap gate. So input I've started with 1. This is 1 0. So at the end we'll have, so we start X on 0, swap on 0 1. So we are swapping both the values. So output of 0 0. So we have 0 1. So if you could see, your this becomes 0 and this becomes, your Q0 becomes 0 and your Q1 becomes 1. Like this you can go for all your gates. See swap gate. This is your control swap gate. All these things you can also work using Composer. You can visualize them using QSphere. Say, for example, any gate here. Let me stop my inspect here. Let me delete. Okay. Add another CX. So now let me delete the CX. Let me take CCX. Okay. I'll show you logical AND here. So here, the third qubit, I've taken it to be 0. And these two as ones. So if my input is 1 1 0, what will be my output? 1 1 1. That is what we had inspected from the beginning, starting from 0 0. So 0 0 0. I'm moving on. First qubit is 1, second qubit is 1, third qubit is 0. So 1 1 0. Moving on. If both my control qubits are 1, my target qubit will flip. So 0 becomes 1. So 1 1 1 is your final output. Do you agree with me? If my input is 1 1, the third qubit is 0, my output is going to be 1 1 0. What I can do for irreversibility is I can apply X gate back, because I'm not measuring these two. For input for 0 0, for 0 1, 1 0, 1 1, various combinations. For 1 1, my output is going to, for 1 1 0, my output is going to be 1 1 1. This is how you implement for all of your classical logic gates. Clear? So working with multiple qubit quantum gates. So just a recap of what I've done till now. So we have seen difference between classical bits and qubits. So classical bits can be in 0 or 1, but whereas qubit can be in 0 and 1 at the same time. How can we put a qubit in both 0 and 1 at the same time? Is by using which gate? Answers please. By using which gate you can be in both the states? By using a Hadamard gate, you can be in both 0 and both 1 at the same time. Irreversible circuits, we don't have a one-to-one mapping between our inputs and outputs. I cannot walk from output to input, but whereas reversible circuits, we have a mapping from one-to-one between inputs to outputs and from output to inputs. And we have seen quantum circuits, creating quantum circuits using IBM's Qiskit. And then the state vector representation, output representations of various visualizations, which we have seen where state vector, Q sphere, and I could also add block sphere representation, histogram representations, and things like we have seen single qubit gates, your Hadamard gate, your X gate, your Y gate, Z gate, S gate, T gate. You can all, when you have time, you can work on with all these single qubit gates and look at your measurements, output visualizations. You visualize your phase change, that is negative phase change in your Q sphere for all of your outputs. And multi-qubit gates, we saw CX gate, CZ gate, swap gate, C swap gate, CCX gates, and so on. Okay.
Okay,
Any
ma'am. The
doubt?
one participant covered out. Sir, unmute your mic and you can ask the question.
Sir, your voice is very feeble for me.
One participant have a doubt, ma'am.
Yes.
Go for reason, sir. Unmute your mic and ask the question, sir.
Yes, ma'am. So like blotch sphere is a tool to visualize the superposition of qubits, right?
I could say not just superposition, represent visualization of any state.
Mm. I'm, I'm actually facing difficulty framing my question in English. Is it fine if I rephrase it in Tamil?
Yeah, no issues, sir. Yeah, proceed. சொல்லுங்க கேளுங்க.
Okay. Okay, ma'am. Actually, like qubits வந்து நம்ம அந்த அது 0 1 1ல இருக்க ப்ராபபிலிட்டி வச்சு தான் நம்ம ரெப்ரசென்ட் பண்றோம்.
0வும் 1ம் ப்ராபபிலிட்டி வச்சு ரெப்ரசென்ட் பண்றீங்க.
ஐ மீன் அது 0ல இருக்கிறதுக்கான ப்ராபபிலிட்டியும் 1ல இருக்கிறதுக்கான ப்ராபபிலிட்டியும் வச்சு நம்ம அதை 2D வெக்டரா ரெப்ரசென்ட் பண்றோம்லங்க மேம்.
இப்போ உங்களுக்கு பிளாக் ஸ்பியர்ல டவுட்டா, கியூ ஸ்பியர்ல டவுட்டா?
நம்ம பிளாக் ஸ்பியர் வந்து ஒரு 3D ஸ்பியர்னால நமக்கு அட்லீஸ்ட் 3 இண்டிபெண்டன்ட் வேரியபிள்ஸ் வேணும்லங்க மேம். ஏதோ ஒரு பாயிண்டர் சொல்றதுக்கு.
ஒரே நிமிஷம். எனக்கு என்னன்னா, இப்போ நான் மெஷர் பண்ணிட்டு எதுல போடுறேன் அப்படின்னா கிளாசிக்கல் பிட்ல தான் போடுறேன். அப்போ எனக்கு அது 1ஆ 0வா இருக்க போகுது, இல்லாட்டி 1ஆ இருக்க போகுது. அப்போ நம்ம இங்க தானே இருக்கோம். நான் வந்து எனக்கு மாறி இருக்கிறதுக்கு சான்ஸே இல்ல. கிளாசிக் நீங்க மெஷர் பண்ணிட்டு நீங்க விஷுவலைஸ் பண்றீங்க அப்படின்னா இட் கேன் பி நெய்தர் 0 or 1 only பிகாஸ் ஏன்னா கிளாசிக்கல் பிட் வந்து எனக்கு 0ல இருக்கலாம் இல்லாட்டி 1ல இருக்கலாம். அவ்வளவுதான். ஓகேவா?
அப்படின்னா நமக்கு 2 பாசிபிள் வேல்யூஸ் இருக்கும்போது நம்ம எதுக்காக ஒரு ஸ்பியரை கன்சிடர் பண்ணணும் மேம்? ஜஸ்ட் லைக் ஒரு நம்பர் லைன் போதும்லங்க மேம், 1D ஸ்பேஸ்.
Okay, good. Nice question. Actually, it is not for just a one-dimensional view. My states can be in any form. My inputs can be in any form. I can change my inputs to any values. இப்போதைக்கு எனக்கு அந்த ஸ்லைடு என்கிட்ட அந்த கண்டென்ட் என்கிட்ட இப்ப இருக்குமான்னு எனக்கு தெரியல. Okay, I don't know whether I have output trees like me. I'm not sure. Actually, எனக்கு இந்த மாதிரி எல்லாம் இது ஒன்னு மட்டும் காட்டுறேன் உங்களுக்கு. I don't know whether it will work right now or not. Actually, because this is from older version of Qiskit. See, this is my code, okay? I'm in a quantum circuit of 1. Upon a 1 less, if I'm having a quantum circuit of 1 qubit, I'm initially in 0. I'm applying x on 0. So what does it do? It takes me to 1. So here, if you look at your transition, I'm from state 0. It takes me to 1. Okay, I'll come here. Now, moving on, what I've done here is I'm applying Hadamard gate on 1. So H on 1, where does it go? It takes me to my plus state. This is my plus. If you remember my PPT notation, this was my Z basis. This is my X basis, and this is my Y basis. So 0, I'm starting from 0, applied X gate. I came here to my block sphere. Now I'm applying Z gate, and it is taking me to this state. Okay, that is my plus. And now again, I'm applying Z gate on plus. So what does Z gate on plus do? It will take me to my minus. Sorry, this is 0, this is 1, this is minus, and this is plus. Okay, why? Because I've applied Z on 1, it takes you to minus. So on minus, if I'm applying Z gate, it takes me to plus. So all these are your various transitions. So it is not just zeros or ones. I'm moving different combinations. I'm starting from 0, moving on to any basis, whichever I want, by just using your quantum gates. Clear? புரிஞ்சுதா?
புரிஞ்சுங்க மேம். Thank you.
Okay. So,
any questions from the participants here? Please raise your hand.
Any other questions, sir?
No more questions, ma'am.
Okay.
So we can continue.
Yes.
Yes, sir.
So these are things which we have seen till now. The next one is this is application of I thought of taking the entanglement circuit, and then I'll talk about this. This is for classical logic gates. I'll show you these things in the demo also. So let me go to my demo. Let me take a new circuit here. I'll show you quantum entanglement here, and then I'll talk about so let me just delete this. So what is entanglement? Quantum entanglement is, as we saw, so till now what we have seen is something called a superposition state, putting qubit in both 0 and 1 at the same time. So that we call it as superposition. So if a qubit is in 0 and 1 at the same time, we call it as a superposition state. Okay. Now I'm applying a Hadamard gate on Q0. Let me take 0 here. Let me also take 0. A 0. I'm applying CX gate here. So this is a circuit, a quantum circuit for creating entanglement. Okay. So what do I mean by entanglement is I'm having two qubits now. If you could see, this is 0, 0 and this is 1. It is in both 0, 0 and 1, 1. Okay. So initially, if I don't have this Hadamard gate, we know the functionality of CX. But now what actually it is happening here is I'm applying a Hadamard gate here. Let us inspect this to make your things more clearer. So I'm in state 0, 0. So look at your state vector representation here. If you want, I can show you the bottom state vector also. So we have two qubits. So this is for 0, 0. This is for 0, 1. This is for 1, 0. And this is for 1, 1. I hope this line is visible. So this is 0, 0. This is 0, 1. This is 1, 0. And this is 1, 1. So I'm starting from 0, 0 initially, applying Hadamard gate on Q0. So what it will do? 0 becomes 50% 0 and 50% 1. So look at the visualization here. So Q0 is in now in state 0 and Q0 is in 1 also. But whereas Q1 is only in 0. So 0, 1, 1, 0. 50% 0 liu, 50% 1 liu will be when I'm applying a Hadamard gate. So we have 0, 0 and 1, 0 here. And look at your state vector representation. This is for 0, 0. That is 50% of time. And this is 50% of time. So 0, 0, we have 0.707, which is 1 by root 2's value is 0.707. Okay. If it is 1 by 4, if it is for all four in superposition of means, we'll be having 1 by root 4. Okay. That value will be showing it here. Next, I'm applying. So now my control qubit is not just 0 or not 1. It is in 50% 0 and 50% 1. Can any one of you predict the output here? If this value is 0, if my top line is 0, my bottom line is going to be 0 only, right? If my top line is 1, my bottom line is going to get flipped. So I'll be having my output now, it is going to be 50% of time I'll be in 0, 0 and 50% of time I will be in 1, 1. So that is what it is going to happen. So this is 0, 0 and this is 1, 1. So I'm starting from 0, 0, applying Hadamard on control qubit. So it takes me to 0 or 1, 50% of time it is going to be 0 or 1. So on my output is now going to be, if 50% of time, if my top line was 0, my output line is going to be 0, 0. The second line is also 0. If my top line was 1, my second line is also going to be 1. If my top qubit is 0, my second qubit is 0. If my top qubit is 1, my second qubit is 1. So here, if these two are entangled now. So if I'm sitting in India, if I'm measuring Q0, I'll get 0. So if I measure, if without looking into measurement, if suppose the second qubit is in US, without measuring my the other qubit, I could say my answer here, since I've got 0, my friend is also going to have 0. If I'm in 1, my friend is also going to be in 1. This is what entanglement is. Clear? So what will happen if this initially we started with 0, 0 and here one qubit is in 0, the other qubit is also 0. If one qubit is in 1, the other qubit is also 1. Now let me give a small twist here. I'm adding plus here. Okay. So now let us inspect here. So the earlier one which I showed is friends behaving exactly in the same way. That is, if I'm sitting here and I'm ordering tea, means my friend will also the waiter will deliver tea automatically to him. He'll also get a tea. But if I'm ordering coffee, he'll also get a coffee there. He need not order. Okay. So that is, we'll have friends, some of our friends will behave exactly in the same way how we behave. There are some friends who will behave in reverse direction. If I say coffee, he'll say tea, ulta ways we have. Okay. So that friendship I'll show you now in case of entanglement here. So let us start with 0, 0. So initially I'm starting with 0, 0. I'm applying Hadamard on qubit 0. So what does it do here is, so this is 0, 50% 0 and 50% 1, and your second qubit is 1. Okay, so that is why it has moved from here to here. Second qubit is 1, full 100% of time your second qubit is 1. Your q0s are now on Hadamard gate, so this is 50% of 0 and 50% of time it is in 1. And now I'm applying CX gate here. So CX, what does it do? So I was here. So if this is 0, 0, this 1 will be converted to 1 alone. So 0 means, so 0, 1, 0, 1, it is going to be the same. But if this was 1, my 1 will be converted to 0. So this now here, if I'm measuring my Q0, and if I'm getting a 1 here, my friend will get if I'm getting a tea, my friend will get a coffee. If I'm getting a coffee, my friend will get tea. So these two friends behave in exactly in an opposite direction. This actually works, this entanglement is a key feature for quantum key distribution, and they have proven for 127 kilometers, they have shown that two qubits are behaving in exactly the same manner or exactly in a reverse manner based upon what inputs you are actually giving. So if your input is 0, 0, if your input is 0, 1, if your input is 1, 0, if your input is 1, 1, you will get 4 different output variations. So this entanglement, or we call it as quantum key distribution, which is being proved for around a distance of 127 kilometers. Okay, so this is what quantum key distribution and quantum entanglement, which plays a major role. Now coming back to my slide, what I've given there is, I've asked you to go for GHZ circuit, a 3-qubit GHZ circuit. The same circuit, which is actually, this was for 2-qubit entanglement was just 2 qubits. If I'm incrementing it for number of qubits, so 1, 2, and 3, I have 3 qubits, so I'm applying GHZ circuit. This we call it as a 3-qubit GHZ circuit. The depth of the quantum circuit and the width of the quantum circuit is what we are actually composing. So here my input will be, all threes are 0, 0, 0, but whereas my output will be, my 3 qubits are in entangled phase. So this is in 0, 0, 0, and will also be in 1, 1, 1 at the same time. Okay, they behave exactly in the same way because I don't have any X applied here. I can apply X for various other inputs and get. So here the depth of the quantum circuit is how many parallelly I'm operating it. So the depth of this particular quantum circuit is, first time I'm having 1, next time having another CX, next time having another CX. So the depth of this particular quantum circuit is 3, and the width is the number of qubits you're having. So this is 1, this is 2, and this is 3. Your number of qubits is your width of your quantum circuit. I'll repeat, width is the number of qubits. If it is a 2-qubit quantum circuit, your width is going to be 2. If it is a 3-qubit, your number of qubits. If it is a 16-qubit, your width is going to be 16. Okay. The depth here I'm talking here is how many operations which I'm doing parallelly on my qubits. I'm having H here. If I have X, if I have another X here, the depth of that particular quantum circuit is also 3. Because H on 0, I'm doing it on qubit 0, X on qubit 1, and X on qubit 2. I can do all 3 operations parallel. So the depth of that particular quantum circuit, H here, X here, X here, and then a CX on 0, 1, CX on 1, 2. The depth of that particular quantum circuit is also 3. Are you getting me the depth definition? The depth definition is the number of operations or the number of quantum gates which I can apply parallelly. I can't apply CX and H parallelly because this value is dependent on this. So I have to apply H on Q0, and then only I can go for applying CX. And after getting this only I can work with this. So the depth of this circuit is 3, If I'm having another quantum circuit where I'm having X here and I'm having X here, that time also my depth is going to be 3. My width is my number of qubits, and my number of quantum gates which I'm using for this circuit is 1, 2, 3. The other one which I've applied X here, X here. So for that, my number of quantum gates will be 1, 2, 3, 4, and 5. Okay. The cooperation or the homework which I'm actually giving you is install Qiskit in a local machine. You need not pay anything. You can download, you can use Qiskit. The pip install Qiskit will install Qiskit, and you can, there are YouTube videos for installation of Qiskit. If you want, I can share the link with the Suguma sir actually. You can implement, you can install it, and you can implement a 16 qubit GHz circuit. So a 16 qubit in the sense I'll have CX applied to next qubits. So 0, 1, 1, 0, or 1, 2, 2, 3, 3, 4, 4, 5, like that, up to 15, 16. Okay, you can apply. But what will happen is your depth is going to be as many depth, right? So we'll have the depth of my quantum 16 qubit quantum GHz circuit is also going to be 16. But the idea or the challenge, what I'm asking you guys to do is, I want you guys to reduce the depth of the quantum circuit to 5. Okay. If possible, reduce and send the circuit to me. Any doubts here? Any doubts in my question? Anybody? Question is
Anybody have a doubt?
construct a 16 qubit GHz circuit and reduce its depth to 5. There are solutions available in the net also. So shall I skip this logical gates, because yeah, I have some more contents to discuss. So we saw quantum entanglement, how to create quantum entanglement, GHz circuit. Optimize in terms of depth is a question challenge which I've given you. Implementation of logical gates. I showed you only for logical AND. My slide contains solutions for logical OR and so on. If you want, I can just have a run through it. So NOT we all know. This is for AND gate, which we saw in the demo. So this is CCX gate. This is NAND. I'm applying an X here to get my output for NAND. This is your circuit for OR. So we apply CCX, CX, another CX. This is your circuit for OR gate. The depth of this particular quantum circuit is depth is 1, 2. All these are done like we actually, the depth of this number of, with this number of things, measurement is also having a depth here. So 1, 2, 3, and 4. So depth is 4, width is 3, gates is 1, 2, 3. Measure is not a gate, it's a operation. So there are 3 gates. This is for your XOR. This is for your NOR. For OR, I'm applying NOT. Okay. Any doubts? Any doubts here? So implementation of classical logic.
One participant is asking the questions in the chat.
Yes, sir. Implementation. So if you're having 2 devices close by, you will have this noise.
Hello, ma'am.
Yes.
Ma'am, one participant put a questions in the chat.
Chat. I'm not able to load my chat, sir.
Ma'am, the question is what is the quantum security and how it is affected single and multiple qubit gates in the quantum?
So what is the question? What is?
What is the quantum security and how it is affect the single and multiple qubit gates in a quantum security, sorry, quantum key distributions?
So what is first part?
My voice is clear, ma'am.
Yes, now it is okay. What is? I
What
understood
is
the second
quantum
part.
security? What is quantum security,
Mhm.
and how it is affect a single and multiple qubit gates in a quantum key distributions?
Mm, quantum security. I'm not sure much about security contents. Actually, quantum key distribution. Uh, See, we can communicate from one. That is, as I told you, sitting here. You can measure the other qubit on the other side without even measuring. You can find the output of that. I'm not sure much about quantum security in this aspect. Actually, sorry, sir.
Okay, no
Mm,
problem. Okay.
okay. QKD related to quantum security. How come single qubits and multi qubits? No, no. Gates are actually fundamental for all of your quantum algorithms, all the things which you are doing. So you actually build your quantum circuit. All your applications which you are solving are based upon implementation of these quantum gates, quantum circuits. So quantum circuits are built upon quantum gates, and you should know the functionality of quantum gates for solving any of your problems which you're having. Say if you are
Okay.
looking into your Morris Manor computer architecture textbooks, all your irreversible circuits, you can convert them into reversible operations. So, and then once when you're building up your adders, your subtractors, your multipliers, you can build complex circuits. So like that, there are various applications. So for quantum music, there are again tools available for generating quantum music. You can generate them. Similarly, for quantum security, I'm not sure about papers, but most probably there you will have something like quantum safe cryptographic contents or something like that. I'm not sure much sure about quantum security.
Okay. Okay.
Any other questions, sir, from the chat?
No, no more questions from audience.
Okay, so I'm just coming on to my end of my presentation. So we have seen these things, how to calculate the depth, width, and the number of gate counts. Okay. So I've just talked about what you can do with this. I just want to share my journey with you people. So if you are really interested to work on with any of these things, I'll tell you how to become an IBM Quizzkit advocate. You have there is a YouTube video of mine. I'll show you that also the link to it. First thing is you have to make contributions to Quizzkit code and community, which is free. You need not for installation or for learning any resources. You need not pay anything. IBM actually conducts quantum challenges twice a year. You can participate in quantum challenges. There are quantum global summer schools which are conducted for free. You can participate in them also. So once when you are doing those things, you get connected with the entire quantum community or Quizzkit community. And the next part was what they ask you to do is probably in the month of January, we'll be having a new application and new set of requirements for Quizzkit Advocate actually. I'll share this link when, I don't know whether my chat is working here. I'll share this link in chat. So I think there is some issue in my chat. I'm not able to.
You share me link, ma'am. I will share it in the group. It's not an
Okay,
issue.
okay, sir. Afterwards, I'll share it for you. I'll share it with you. You
Okay.
can register all these links. I'll share with you. So this is
Okay.
the link for if you're interested to become an advocate. You can register here. They will mail you once when the application forms are opened. So what they do here is they look into your contributions, what you have made. So whatever you have done, if you have attended a quantum computing training, that also has marks. If you are giving sessions, if you're connected in Slack, everything has contribution marks. Okay, my one of my video will talk about that. So you can just do this, and what they do is if you're having enough amount of contributions, they send you vouchers for taking up this exam. This exam cost is around $200 in India. It is around some 180, but they send you a voucher for $200. We need not pay, they send you vouchers, and you can take up the certification exam. And once when you clear the certification exam, they will select you to become an advocate. Okay, this was what had happened earlier, but now there might be some changes. One second, sir. This you can register here. Once when the application gets open, they will send you a mail, and you have to take up this examination if vouchers are sent. Okay, so preparing your examination voucher, for preparation of that, again my video contains what all the things are needed. So maybe there might be some changes for the next upcoming Biscuit Advocate things. So this again, I'll share it with sir. So this is the place where you can, I'll show you my Slack. And this was a link for creating IBM ID, which is free actually. The Slack channel, which I have it here. So, and this you have a plenty amount of channels which are available. The locked channels are for only advocates, or if I'm a mentor for any of these challenges which is happening. So we have global summer schools happening. We have spring challenges where we become mentors. And this channel, I would like to go for Biscuit Advocates application. If you're interested, if you can just browse this, be active in this particular channel. You need not even measure things. So this was the latest message which we got recently. So they are going to relaunching the Biscuit Advocate program every early next year, probably in 2025. This is for my Tamil channel. I'm a translation lead for Qiskit textbook. Right now it is inactive because of Qiskit transformations from one earlier version to 1.0 version. And these are my private chats. So I would like to say, go for India channel. You can look into all these various challenges which are coming in. You can just register here, and you can get links, access to the channels which are for normal people. And again, I repeat, all these are free. Okay, we have a textbook channel and everything are available here. So this is for Slack channel, and this is my quantum IBM experience. And why you should become an advocate is you're connected globally with n number of like-minded people. Earlier, I was single person working on quantum. I was having very few people who were of my taste. That too, specifically from computer science background. I was having very few people. And so now I'm connected globally with various Qiskit advocates, and not just advocates, various other quantum experts. So advocate mentorship program is one, quantum Qiskit global summer schools, IBM quantum challenges, all are free actually. Even our fall fest, which we organized at CIT, was free for the participants. We actually invited students in last 3 years continuously we conducted. Being an invited speaker as I'm here today, I'll be invited for, I've delivered nearly around 30 to 40 sessions till now. And we have something called as Advocate Cafe, where I'll be paired with another advocate every week. And that is also a quantum algorithm. My pair is random. So we connect together and we share our interest, what they do, what we do. And whenever I'm stuck off or when I'm having any doubts, I have an entire community supporting here. Okay, I'm not working, my research is not all alone. I'm actually connected with people and we work. And there are IBM internships for students, and even for, if you're an advocate, they give you can either go for hardware oriented internships or software oriented, and obviously new collaborations. I'm mostly connected with all India Qiskit startup companies. We collaborate and we work for research papers. We work for real use cases actually. And the courses which I have done, I became a Qiskit advocate from September 2020. Later on, earlier when I did, certification exam was not a requirement. We had a test which I have to take. I took up the test, cleared it. I had an interview for 1 hour actually. My interview was very cool. And after that, they released this certification exam. And I took that certification exam in probably in November 2020. And after that, I was in various challenges, mentor in global summer schools and so on. I actually did these courses. Again, this Q course, keep an eye on LinkedIn. They do post Q courses, which is free. You need not pay anything. This is available. We collaborated with the University of Latvia. And there was another course which was from Classic. I showed you a Classic tool. I'll show you the demo if I have time. So again, these are actually we applied. You have been shortlisted for those courses. So here we were around 60 global people who did this particular course, and it was collaborated with Classic. Just like Quiskit, Classic is another tool. So here, again, Omanium and Q World are collaborating, and they are actually giving scholarships. So I received a scholarship of $900, and we worked on Q Zinc. I got certificates for all these Q Mercury, Q Nickel. These are various quantum circuits which are available, and all are free. I've not spent any money in doing any of these courses. So it is available in LinkedIn. Even mostly when if it comes in, I'll also repost it. If you're interested, you can follow me in my LinkedIn page. And this is again 2024. Recently, I completed this using QWorld, Quantum, and Artificial Intelligence. So honors received. These are my entire badges. The Gridley badges which I have received from IBM. And this is the project which we did we also we collaborate and work on quantum mentorship programs. And I was invited for celebrating women working in quantum in India. I was an invited speaker where I spoke about my quantum journey, what I've done till now, the link for that. And these are some of the references which I've used. This was the first textbook which I never forget, and a very difficult textbook to follow actually, Nelson and Chang's textbook. And this was my after for entire my MS, I was working only on this textbook. Okay, because that time we didn't have much amount of. I started from 2003 working in quantum computing, and this book was published in 2000. Really, it was a very challenging time for me. Thought of even not to do PhD after completing my MS because it was such a I would say it was so difficult to work on an area where no one is working, and everyone do scare me like, why do you work in an area where you don't get to have something which is going to come in future? You don't know whether it is going to come or not. But the fantasy of what I've learned, whatever things which I've did, made me not to leave this area actually. And now I'm really happy. Okay, something I've done, and I'm doing it for my younger generation, my student community, my students. I do share the difficulties what I've faced and the challenges which I've overcome, and I'm here right now. Okay, and this is for reversible computing paper textbooks. Really a very good textbook. I started reading these books for my PhD works, and I worked on various simulators at this period, like Qt Pro, QC Viewer. All those tools are really wonderful. I could visualize them, visualize superposition states, and work on. I can work for n number of qubits, like 200 qubits. I could work because they are just simulators. But now from 16, 17 onwards, I'm working on devices. I completed PhD in 2015, where I didn't have any devices at all. But now I'm happy to work on real quantum devices. IBM is giving 127 qubits for Qiskit advocates. We worked on a problem on qubit 127. So imagine 2 to power 127 values I can compute at one point of time. So that is again very good. James is my friend. He's a person whom I spoke about earlier. He's working on quantum music. He's learning Carnatic music actually to produce papers for quantum music. Just browse through. Frank and James again, they work on this Qiskit Pocket Guide. They work on quantum what was that, quantum music. And they also we have Qiskit 1 minute videos. If you're interested, go through Qiskit 1 minute videos also. Just a 1 minute video where they talk about one particular concept. And this is our playlist, CIT Quantum Hackathon. We had around, this was for the year, I think it was 2022. We had around 26 speakers, and all the speakers they readily accepted our invitation from all over the world. It was online, and we have our recorded sessions for that. And here I would have spoken about how to become a Qiskit advocate in this YouTube series. And these are some of the other reference papers. And these are papers which we contributed. We have a paper on quantum drones. This was my SMG gate where I worked on 2's complement adder subtractor with overflow detection logic for quantum computer-based systems. And these are some of IBM experience exploring quantum concepts. And this is for quantum drones paper. And there are some more papers which I'm currently working on. I've not posted it. And these are my repositories. Someone was asking for quantum machine learning. Actually, this was Nati is from Classic. We worked on designing interactive introduction to quantum computing course with Classic. So this is also a wonderful team actually. Alvaro, Rishi, all these people connected globally, and we did this project last year. And this for performing arithmetic operations from Hitanshu Vardhan, and I was a mentor here. And Jay Kumar, he's one of the speaker. He'll come probably next week. And we collaborated for working on tutorials for machine learning. And this is another repository where you will find applications using. So here, this was where we worked on course outcomes, attainment of student course outcomes here. You could find the contents here. And this was a lab manual, which I coordinated with Guncha. And Julian, my person who taught me so much actually. He's from IBM Switzerland. And Mandas was another one of my colleague. We collaborated for arithmetic circuit library. So there are many things you can explore. You can find applications. You can do research. And these are some of the additional references if you're interested. What is fundamentals? What is Qiskit? What is for computer science people? History behind quantum. I'm not talk. I didn't spoke anything about quantum algorithms. Quantum algorithms are really wonderful. You could do massive tasks using quantum algorithms. And by this, I'm coming to the end of my talk. You can reach me. My mail ID is this, and you can follow me at in my LinkedIn page. Thank you all.
Thank you, ma'am. So, when participants, this is an end of session. So, if you have any questions, please raise your hand. I think no more questions from audience side. So, today's session is a very wonderful, ma'am. You are explaining very practically, which was very useful. Thank you, ma'am.
Thank you, sir.
Thank you. Now we are going to conclude this session. I would like to invite Kausalya, Assistant Professor in Physics, to deliver the vote of thanks.
Good afternoon, all. It's my privilege to propose vote of thanks on this 7-day online FDP program on quantum computing for next generation under DPT Star College scheme. I would like to thank our institution head, CEO, secretary, principal, vice principal, dean, research and development for their constant encouragement and support to conduct this FDP. And I extend my gratitude to Dr. S. Raja and Dr. T. Velumani, head Department of Computer Science, and Ms. D. Uma Mageshwari, head Department of Physics, for this fabulous session. I convey my sincere thanks to our today's resource person, Dr. Manjula Gandhi, for sharing your time, knowledge, and enthusiasm with us. Your presentation has sparked curiosity and motivation to delve deeper into its fantastic field. I would like to extend my thanks to department faculty members and the organizing committee for their immense effort towards this event. Lastly, I would like to thank all the participants. With all your support, the 4th day of this FTP event is completed in a successful way. Thank you all.
Thank you, ma'am. Thank you for all of you joining today's sessions. I will post the feedback links shortly. Please share your feedbacks for the today's sessions. Thank you, all of you, once again.
Thank you, sir.
Thank you.